Alright, here's a video for lesson 61, Pythagorean identity proofs. Now, I'll go over the basics, but the ideas are the same, while the questions will all be a little bit different, a little exploratory, okay? So, the tools that we need are the same, though, so we'll go over those first. Now, I need to know what tangent is equal to. Tangent, tisk, is what I keep saying in class, TSC. So, tangent is equal to sine over cos. Now the other three functions, we call them the cofunctions, are secant, cosecant, and cotangent. If you can spell them, the third letter will tell you which function it is the reciprocal of. So this is a C. Secant appears to be 1 over cosine. Cosecant, third letter is S. Cosecant is going to be 1 over sine. Cotangent, third letter is T, it's going to be 1 over tangent. Now that's the reciprocal of tangent, right? And reciprocal means to flip a fraction. So essentially, instead of writing it as 1 over tangent, I can refer back to this definition. I can flip this, and I can say that cotangent is also equal to cos over sine. Now, we always write our coses and our sines and our tans squared. We put the square on the cos, or on the trig function, not on the theta. Theta is just like x, by the way, so this is really the same thing as this. Now, the Pythagorean identity. This needs to be memorized. Cosine squared plus sine squared equals 1. Now, sometimes it'll change the order. It'll say sine squared plus cos squared, but that's the same thing. Addition is commutative, meaning that you can change the order and the truth of the statement. Alright, now the other Pythagorean identities. Let me remind you guys how to solve for these real quick. For both of them, I'm going to have to start off with the original, so I need to have that memorized to find the other two. And what I do here is I'm going to first divide by cosine squared on all terms. So this is cos squared, divide by cos squared, and divide by cos squared. Now, cos squared over cos squared, anything divided by itself is 1. Bring down the plus sign. Sine over cosine, we have that written up here. Sine over cosine is tangent. So since these are squared, this is going to be tan squared. And 1 over cos is, we wrote it up top already, it's secant. So this is secant squared theta. That's the second of the Pythagorean identities, in no particular order. And now let's do the other one. Start off with the original Pythagorean identity, and we're going to divide everything by sine squared. Cos over sine, we wrote that down. That's cotangent, cot squared theta, plus sine squared over sine squared is going to be 1, is equal to 1 over sine squared, which we have written up top, is cosecant squared theta. So those are the three Pythagorean identities. Now I'm going to keep referring back to these, so that's why I wanted them on this sheet so we could use them. You should have the first one memorized, and the other two you should know how to solve for them. Now the idea of these proofs is we split them, we make them a left-hand side, right-hand side proof. So we split them at the equal sign, and we prove on one side that this is equal to this. And the goal always to prove that it's an identity. So you're proving that it is a rule that is always true. So you're proving that it's true. You're proving that they're equal. I have a few selected, but I want to show you guys the three main steps, the three main techniques first. We had these written down in our notes. If you don't have them, your toolkit is empty. Your toolbox is empty, and so it's going to be difficult to do anything. Here are the general tips for trig proofs. We're always going to break all the other functions into cosine and sine. We're going to look for the larger side of the Pythagorean identities, so these red ones. We're looking for sine squared plus cos squared. We're looking for 1 plus cotan squared, or tan squared plus 1. We're looking for those, and we can substitute because they're equal for this whole thing here. That's the idea. So we can turn two terms into one. Whenever I see squared trig functions, I get a feeling that it might be one of the Pythagorean identities, and then I refer to my little list. when we're adding or subtracting fractions, we may need to get common denominators, and what we do then is something that I call the best-fits-all method. And what that means is if I had two fractions, let me get this out the way. What that means is if I had two fractions, say I had 1 over x plus 1 over y. What I would do is I would take this, and I would multiply it here and here, and then I would take this, and I would multiply it here and here. And as you see, that's going to get me the same denominator, yx and yx. So that general move works for any time we're adding fractions, and we don't know how to get them to have common denominators. That'll work. Okay, now I'm going to do 3 examples with you guys. I'm going to refer to which one of these bullet points I'm using while I'm doing it, but keep in mind the only way to get good at these is to practice them because they require a little bit of creativity, a little bit of thought. They're not very straightforward. All right, now I've picked 3 from this handout that I'm going to do with you guys, and those are 16, 15, and 17 in that order. Now, for question 16, I've split it. They wanted me to prove that this is equal to this. Now, on the left-hand side, I have a bunch of trig functions here, and I'd really like it if I could break them all down into sine and cosine. So I'm going to take secant. Secant is equal to 1 over cosine. Minus sine, which if I want to make it into a fraction, just becomes sine over 1. Times tangent, which is sine theta over cos theta. Now I have 3 fractions here. I have subtraction and I have multiplication. Multiplication is going to come first in PEMDAS, so I'm going to multiply top times top and bottom times bottom. Sine times sine is sine squared. 1 times cos is cos. I'm going to bring down the original term here, and the minus sign, and that's where I'm at right now. When I have 2 fractions with like denominators, I can just smush them together. When I smush them, what I mean is I'm going to take the top and put it all over the denominator. What's my common denominator? Cosine theta. And now this, it's 2 terms, it's got a sine squared in it. That feels to me like a Pythagorean identity, but I'm going to have to take a look. 1 minus sine squared. Let me look. Now if I look at this, copy this out. Ooh, that is not what I want to do. Copy this out, put it all over some white paper here. I got more scratch work here than I thought. Alright. Now remember, what I had and what I wanted was I wanted something that said 1 minus sine squared theta. That's what my numerator was in the question. Alright, so keep that in mind. Now my 1 is over here, but my sine squared is all the way over here. So if I wanted this to read 1 minus sine squared, I would have to minus sine squared theta over here. But if I did this on the right side of the equal sign, and I put that over there, I would need to do it on the left side of the equal sign as well. So I'm allowed to do anything as long as I'm doing it on both the left and the right of an equation. So these sine squareds, plus and minus, will cancel each other out. And just by a little rearranging with subtraction, I get a manipulation of the same rule that says cosine squared theta equals 1 minus sine squared theta. So that means that 1 minus sine squared theta can be substituted in as cos squared theta, since they're equal. Let's go back. That means this right here is equal to cos squared theta. That's still over cos theta, of course. And if I have the same thing on top and bottom, I can cross out a cosine theta with one of the 2 cosine thetas. This right here is technically cos theta, cos theta. and I can cross out one of those, leave me with one behind. The way that I write that typically is just by crossing out the square. And so this leaves me with cosine theta. And just to keep everything copacetic, I'm going to keep that orange. And now look, my left-hand side equals my right-hand side. So I can just simply state LHS equals RHS, W to the fifth, or QED. You can pick which one of these you feel like putting. Now let's do another. Question 15. If you want to backtrack and watch that one again, if you were iffy about it at all, that would be a good idea. Sort of rewind back and watch that again and make sure you understood all the steps involved and how I got there. But let's start 15. Alright, I want to prove that this is equal to this. It looks like I'm going to have a lot of terms to change here, so let's get to it. I think this looks to me like distribution on the left, right? Something outside of parentheses. Cos times cos is going to be cos squared theta, and cos times 1 is going to be plus cos. And then I'll bring this down, plus sine, accidentally screenshotted, alright, plus sine squared theta. Now, I've said this a few times, addition is commutative, which means I can rearrange the order of things, and it'll be fine. So if I want to, I can move this sine squared up, cos squared theta, plus sine squared theta, plus cos theta. And I hope you see that this is a Pythagorean identity. Cosine squared plus sine squared equals 1. So 1 plus cosine theta, and that's really the simplest I think it's going to get on the left, right? So I sort of circle this. I don't think there's anywhere else for me to go here, so I'm going to leave this alone. Now let's attack the right-hand side. When I have two things added on top of a fraction, right, I would love to cross out these tans, but it doesn't work like that. What I need to do is I need to split this into two fractions. So I can get sine over tan, bring down the plus sign, and tan over tan. Anything divided by itself is going to be equal to 1. So tan over tan is 1. What I really need to do is I need to take another look at this, sine over tan. What happens here, and I'll keep it green so you can follow along with what I'm doing here, I've got sine over tangent. Tangent is equal to sine over cosine. So let's rewrite this. So I've got sine over cos. Sine over tan, which is sine over cos. Okay, got it. Now whenever I have fractions, right, I don't divide by fractions. What I do is I change, and I flip. So I'm going to keep the sine theta. So if I wanted to, I could call that sine theta over 1. Change it to multiplication, and then flip this. So instead of sine over cos, it's going to be cos over sine. Let me not forget my thetas. Now, sine and sine will cross out, leaving me with nothing but cos over 1, which is just cos. So I've got cosine theta. Oh my goodness, look at this, plus 1. 1 plus cos, cos plus 1. These are the same thing. So I can rearrange them if I want to, but it's obvious, so I don't have to. My left-hand side equals my right-hand side. Q, E, D. Okay, I'm done with that proof. The idea is always to take the more complicated side and make it look simpler. It's better. So I'm going to be attacking mostly this side. This side is easy, cotan of x, but this side right here looks complicated. So I'm going to attack this one more. Now let's prove that these two are equal for question number 17. First thing I see is this, 1 plus tangent squared. I've seen the Pythagorean identity so many times, I think I'm pretty sure this is equal to something. So let me check. 1 plus tangent squared. Oh yeah. So 1 plus tangent squared is equal to secant squared. So I can substitute in. Right here. Okay. So this right here is going to become secant squared. Oh, they're using x instead of theta, so I'll just keep with the x's. Secant squared x. And this still has tan x cosecant squared x. Alright, I made my substitution. Nothing's crossing out or anything, so I think I may have to change everything into sines and cosines now. I'm going to keep the numerator black and I'll keep the denominator red so we can keep track of everything. Tangent becomes sine theta over cos theta. Cosecant squared, cosecant's 1 over sine, so this is 1 over sine squared. Oh, I keep changing back to theta out of habit. Let me keep these x's. You can change them if you prefer it, it doesn't matter, but I'm keeping with the question. So this is 1 over sine squared, all over secant squared, which is 1 over cos squared x. Now, since these are attached with multiplication, they're basically like one fraction already. So here's what I'm going to do. I'm going to, oof, I'm running out of room. I should have written smaller. So here, I'll crunch this up a little bit. Okay. Now let's keep going. What I'm going to do is I am going to keep, change, and flip. So I'm going to keep the sine x over cos x times 1 over sine squared x. I'm going to change it to multiplication, and I'm going to flip the 1 over cosine squared x. So cosine squared x over 1. Now let's see, I hope something crosses out because these are all fractions attached to multiplication, and that's usually what happens here. So let's see. I've got a cosine x here. I've got 2 cosine x's here, so I'm going to cross out one of them, leaving me with a cos x. I've got a sine x and a sine squared x, so I can cross out a sine x with one of the 2 sine x's here. Let me rewrite once. So I've got 1 times cos x over sine x times 1. 1 times cos is just cos, so this is cos x over sine x. And that's really the simplest I think this is going to get, so I'm going to leave it like that. Now, let's see what we have on the other side so I can remind myself what the goal was. I had cotangent of x. What's cotangent equal to? Let me check again. Cotangent is equal to... oh, cos over sine. So this right here is equal to, by definition, cos of x over sine of x. And look, my left-hand side equals my right-hand side, which was what we wanted, or QED. Alright, so you have 2 handouts full of these. They're also on mrjcostello.com. You can go to Algebra 2 files to pull up handout 61 and 62 if you'd like to practice these. Pick a handful of them, pick ones you know how to do, and remind yourself that you do know how to do them. Pick ones that you don't think you've ever touched before and see if you can figure them out. They're like a puzzle. They get easier the more that you practice them. So practice away, good luck, and I will see you in class.